All right, so my name is Mohammad, and we're going to talk about real-time signal analysis. Just a background about myself. I'm an application engineer at ThinkRF, and ThinkRF is a small company in Ottawa that makes wireless spectrum analyzers. I've developed APIs and GUIs in C, C++, Octave, MATLAB, Python, LabVIEW, Visual Basic, and I'm starting to learn a little bit of C# right now. So I have an understanding of all the other tools that's used for spectrum analysis, like real-time signal analysis. That's my email if you guys have any questions. That's my GitHub page if you guys want to check out any of my projects. And my main interests are signal processing, mainly biological. I like to do wireless too because it's my job. And at the bottom of the slides, you can see that GitHub page that has all these slides. So if you guys want to go there and keep track, all the source code is on there too. Like I'm not going to go through the code because it's just going to be too long. But I will demonstrate what they look like. So the schedule for this talk is first I'm going to talk about the intended audience. Then we're going to define a signal. Then we're going to talk about signal analysis, why we should use Python for signal analysis, and then we're going to demo. So the slides I'm going to actually go through very quickly, just so we have enough time to go through all the demos. So you can look at this video later, or if you can look at the slides, just see what I was talking about. So the intended audience is for beginners, anybody who is beginning a hobby in electrical engineering. So if you want to get your ham radio license, or you want to make bioamps, or if you want to do anything like that, this is for you because Python is free. So you don't have to buy a $2,000 or a $10,000 tool just to get your signal analysis going. It's for hobbyists. So if you're already a hobbyist and you're looking for a new language to look at your signals, whatever they are. And finally, it's for professionals. So I'm also going to actually show the application that we make at ThinkRF, and it's all built on Python. And it'll show you the capabilities that you guys can do when it comes to application development. So what is a signal? According to Wikipedia, it's a function that conveys information about the behavior and attributes of some phenomena. So these could be RF signals, so your Wi-Fi, FM radio, AM radio, and these are the ones I'm going to demonstrate today, and a proximity sensor. The other thing is audio signals. You can convert an audio signal to an electrical signal and then analyze that. Finally, electrobiological signals, so the heart rate. We're going to look at that too today. I plan on having an ECG, but the ECG sort of broke down and transformed into a proximity sensor. And I have a pulse rate sensor to replace it. So you'll still look at some heart signal, I guess. What is signal analysis? So it's the process of acquiring a signal, then processing it, packaging it in a packet or just a regular value, spit on a serial, and then and you should usually use hardware and software. You can't really just do it with software alone. So you start with your signal. It doesn't matter what it is. It could be biological, it could be chemical, it could be anything. It goes to your hardware and then goes into your PC through either the network, a USB, or some sort of API, so like a PCI API or some special hardware attachment you have. So first, you're in the analog phase. You apply some gain or attenuation, depending on what your signal is. Then you clean it. Clean it could mean a lot of things. It could mean filtering, down conversion, IQ modulation. It could mean all kinds of things. Then you digitize it, goes into an ADC. Then you clean it again with some digital signal processing. So that could be some decimation, frequency shifting, going through all kinds of CIR filters or FIR filters. And then you finally send your data either in some sort of packet or print it off serial or whichever way you find comfortable. On your PC, you want to read your signal, clean it up, and that's your final amount, the final type of cleaning you can do. So that includes things like IQ offset corrections, computing the FFT, computing the power spectrum, DC offset corrections, all kinds of stuff. Visualize your data. That's kind of important just to make sure your data looks good. And then you compile. And by compile, I mean you could either turn the whole thing into an executable and just give it to a customer, or you could store all your data in a database, put it in an Excel file, put it in a CSV, whichever way you want to do. And finally, you have your signal on your PC. Why you should use Python? Python is free. Now, I know I'm preaching to the crowd, but this is a big deal in our industry, in the electrical engineering, because most of the tools are very expensive, and all the attachments are also expensive. So a base model for one of these tools would be $10,000. And every single attachment, so let's just say the equivalent of NumPy is also $10,000. The equivalent of Twisted is also $10,000. The equivalent of SQL is also $10,000. So it can really add up. Flexible, you can actually put it through all kinds of different operating systems. If somebody wants to run Windows, you can put it on Windows. If you want to put it on a Mac, it'll run on Mac. If you want to put it on Linux, it'll run on Linux. It's a high-level language. Again, that's really important for real-time signal analysis because not everybody can read lower-level type of stuff. There's a lot of open source libraries, and that sort of goes back to being flexible. And some of these, the ones I use, is PyQt or PySide, just for GUI development. NumPy and SciPy for all the math. PyQt Graph is for the visualization. And depending on how you want to acquire your data, so you can use PySerial if your data comes through a serial. You can use PyUSB if your data comes through USB. You can use Twisted or Tornado if you want asynchronous sockets. And there's also the built-in Python socket functions, which they work fine too. And there's a great community. So you can, if you have any problems, it's really easy to find answers just because there's all kinds of Stack Overflow questions that have been asked. So this is what it looks like. If you want to read your data, you could either call functions from C or C++. You could use PyUSB sockets, PyAudio, or PySerial. That pretty much covers everything because every device you buy is going to come with a C or C++ API. And if you don't like that API, that's the point where you write your own API for it in Python. To clean your data, you use your mathematical libraries, so NumPy and SciPy. To visualize it, you could use PySide, Matplotlib. I kind of don't like Matplotlib, and PyQt Graph. So how many of you guys have actually heard of PyQt Graph? OK. So today you're going to learn a new library to visualize your stuff, and I think it looks pretty cool. Finally, you compile it. So again, you could either make an executable and distribute it among customers. Most of our customers are on Windows, so you give them an executable. You can save your data with XLWT into like an Excel spreadsheet, or you could just put it on an SQL database. OK. And now we're going to go through the demos. So the first one is the application that we make at ThinkRF called the Real-Time Spectrum Analyzer, the RTSA. And I don't have our product here. It's called the WSA 5000. It's actually at work. So what I'm going to do is I'm going to connect to it through the internet. And you're going to be looking at Wi-Fi that's in Ottawa. ThinkRF.com. Nope, that didn't work. I misspelled it. Nope. What the hell? Okay. OK, so we're going to skip that part of the demo because that didn't work, but we could try again later. So instead, I'll demonstrate the RTL SDR. So this is a software-defined radio. You can buy it for 20 bucks. So if you don't want anything too expensive, plug that in there. And basically, I'm going to use a C library that somebody in open source developed. And then somebody made a Python wrapper on top of that C library. You can check it out on the GitHub repo. And you'll see how that'll work. So OK, so what you guys are looking at is two PyQt Graph plots. And the top plot is time domain versus voltage versus time of an IQ signal. And this right now I'm tuned to, I think is 99.9 FM. It's a radio channel here. And you can sort of see the FM modulation going on. I don't know if you could. I don't know if you guys have that experience, but I could. Every time you see that little bump, and then it goes up and then it goes down, it goes up and goes down. That's FM modulation. And at the bottom is the power spectrum versus the frequency domain. So I applied some IQ correction, and then the FFT, 20 log of the FFT. And that's what that wideband signal. It's not really that wide. It looks wide because the sampling rate is so small on this thing. It looks really wide, but it's actually not. So if I actually move this up, I'm hoping I get something more, but it doesn't look like it. It actually went lower. It's a little bit better down here. It's pretty interesting. You can sort of see how it changes when I put my hand all over it, because now it has to go through this. The FM radio signal has to go through my hand and then into the antenna. So it sort of acting as, it's adding noise more than anything else, so the whole spectrum is going up. So that's one demo. The next demo I have is a pulse sensor. So I'm going to be sensing my pulse. Just got to connect this. So again, in this case, the sensor here is this little guy. It's emitting a light. And I don't know if you guys can see it. That's the light. And that light's going to go through my finger. On the same sensor, there's a photoresistive transistor that's going to read back the light that it reads. And basically, that light's going to change every time my heart pumps blood into my arm. So every time my heart beats, it pumps blood into my arm. The blood gets thicker at the tip of my finger. So that means the signal is going to go down, and then it's going to go up, and then it's going to go down, it's going to go up, and it's going to go down. So yeah. So ECG plot serial. So what I'm using here is PySerial to grab the data from the serial port. So I'm just going to maximize this. Yep, and it's too low. There. So that is my pulse. It's not normalized, so it's not that easy to tell, but let's just let it keep going. Okay, that's my pulse. And you can sort of see it's beating really, really high because I am nervous. But yeah, that's the pulse. You can't really tell much from it other than that I'm alive, but so I guess that's cool. All right, so that's another demo. Now, this was actually my backup plan because I had an ECG monitor. It's this little red guy over here. But I fooled around with it yesterday, and I think I blew it up. But instead, it actually turned into something not as cool, but still cool enough to show, and I'm hoping it works. It turns into a proximity sensor, and I'll explain that in a second. Okay, so let's just make sure this. So it's really important to get your grounds and your source right, because if you don't get that right, you blow it up. And that's what I did, because on the Arduino, the 5.5 volt pin is right beside the 3.3 volt pin, and the thing takes, oh, okay, and the thing takes 3.3 volts, and I'm pretty sure that's how I broke it. All right, so now it's working as a heart rate monitor, but I don't want that. So I don't know if you see, every time I put my hand closer to it, the signal sort of gets thicker, and when I take my hand away, it gets thinner. I'm not touching it, right? I'm just sort of getting really close. So the phenomena there is that it's picking up the 60 hertz power and the 120 hertz fluorescent light. And because there's an open circuit, that little solder joint is actually transmitting a signal, right? And whenever I put my hand near it, that signal gets reflected back into the output, right into my Arduino, and into the screen. So this is called a proximity sensor. It's not really, it's accidental, but a real one would work a lot better. So again, we'll just do that one more time. Put my hand closer. So I touched the wire, so that doesn't count. But put my hand closer. You sort of see it get a little bit thicker. Take my hand away. It's thinner. And this is similar to radar technology. So on the Tesla and the new Mercedes, you know, those self-driving cars or the self-correction cars, they have a bunch of sensors on them, and one of them is a front radar sensor, so it keeps sending radar waves, and it reads them back. And when it gets something back equivalent to its original sensor, it knows that something's in front, and it should stop or it should watch out for it. All right. So let's see what else I got going on. I'm going to try dialing into our unit one more time. All right, so it is working. There, okay. So this is the main application that we develop at ThinkRF. Everything you see here is built on Python, so the entire GUI is using PySide. You can also use PyQt if you like. PyQt graph is all of our plots, NumPy and SciPy to do all the data analysis, and finally Twisted to do all the asynchronous socket reading. So there's like nobody in the office right now, so I can't really show you anything cool. If I had it with me, I'd be able to show you Bluetooth and maybe cellular. But for now, we're just going to look at Wi-Fi. Okay. So if you guys don't know, Wi-Fi is usually at 2450 megahertz. We have a 20 dB attenuator, so I got to turn that off. And there. So you can't see much because A, it's really slow transferring all that data from Ottawa all the way here. And also, because it's also capturing noise, so Wi-Fi isn't active all the time, like that FM signal was. It's active and then deactive, active and deactive. So what we have is, in our FPGA, a feature called triggering. So we specify only capture data when a signal is within this range, and that range is this box. Again, this is all Python. You can have a little box that moves around and trigger. Again, with PyQt graph, you can have more than one trace. So I can add another trace, make it an average. So that's that yellow, that's the orange one in the front. I can add a third trace, I'll make it like a max hold. So it's always holding the maximum. I can have another trace and just sort of hold it, so it just stays the same. And if you want, you could change the color of your traces. Let's pick something. Teal is already there, blue. So the one over here just turned blue. We also have markers, that's there, and the marker value is over there. You could change the marker to a different trace or whatever. And again, everything you see here is in Python. We also have some visualization. Spectrogram, it's always a cool one to look at. So this is the signal over time as it goes down, and this is pretty good for detecting interferences. So if there's a signal that's hopping, you won't be able to see it on the top trace, but if there's a history, you'll be able to see it at the bottom trace. And the other one is persistence. So that just shows you how persistent your signal is. The more red it is, the more available it is. As it turns blue, it means it's slowly fading away. And again, you could change the colors of these things if you like a different color. Other features we have, you can save your data to a CSV, or you could just save it to our own VRT type file, and you could just read it back later. Yeah, so that's this application, and the final demo is audio. So using PyAudio, you can actually read audio signals. Where's that? You can actually read audio signals from your sound card. Sorry, I just got to find my aux cable. It's somewhere here. Okay, there it is, under the thing. All right, so I'm just going to do a quick test. Make sure. Okay, let's pause this. So this is the audio signal, and that's me talking right now, but that's the audio signal coming in from my microphone. One neat trick is, can I whistle on this, or should I? Okay. If you look at the bottom trace, you could sort of see that there, and that's just me whistling. Actually, there's a man here with a harmonica, which I found practicing. So if you could just do what I told you to do. Yes, sorry. Yeah, so that note right there, was that the highest note? So the one you see, that last pop, that's the highest frequency that his harmonica can go up to. But the sound card can go even higher. This is a video of 20 hertz. I mean, it's basically a human audio test. So let me connect the aux cable. So I'm basically going to take that sound out of my sound card and into my mic. So right now it's at 33 hertz. You can't see it because my sound card is really bad at these lower frequencies. You see a signal, but it doesn't really pick up, doesn't know what's going on. So it's basically this thing right there. If I move this up a little bit, you'll be able to see it. And what's happening here is that it's saturating because my volume is too high. So let's go down a bit. It's not saturating anymore. I'll reduce the volume here. So you can sort of see a clean sine wave, right? And the reason why this is so clean is because the frequency is very low. It's at the edge of my spectrum plot. So it's further away from the Nyquist frequency. And the Nyquist frequency is the highest frequency that your ADC can actually read. If you go any higher, then you're going to get something called aliasing, and we'll talk about that in a minute. But as this goes on, if I was to fast forward through the video, you sort of see the sound wave gets way more ripply, so it's not sinusoidal anymore. That's because we're actually closing in on the Nyquist. And as soon as we hit that, right, so that last bin over here, as soon as we hit that, that thing going back is called aliasing, right? Because we can't detect a signal with a frequency higher than half of our sampling rate. What we get is this, and that's just distortion. And that's why you should never inject a signal higher than half your sampling rate, because you don't know what you're going to look at. You're just going to get all kinds of weird phenomena like these. The sampling rate is how many samples that your whatever your ADC is can actually read per second. So if you read, let's say, 1 megasamples, so that's 1 million samples a second, that means you can only look at 500 kilohertz of frequency. If you inject anything higher than 500 kilohertz, you're going to get that effect, that aliasing. And the way you do anti-aliasing is you put a filter right in front of your ADC to stop anything higher than that specific frequency from getting in. That's the main way to do it, and you do that in hardware. So I'm pretty much done for this talk. And if you guys have any questions, please let me know. I think you have to go down to the mic. Or
I can just shout it out.
Do we need people to come down to the mic for
We need it for the video. For the mic.
Yeah, if you could.
Hi, I was just wondering, like, you said you have a software-defined radio dongle there for picking up signals. What would be a similar kind of device if you want to mess with transmitting and receiving? You know, sort of low-budget transmitter receiver for attaching to a PC or...
Before transmitting anything, you have to actually get a ham radio license. You're not allowed to transmit unless you own that band or unless you have a ham radio license.
What if you don't care about that?
This is actually...
I mean, is range as well might be a factor if you're doing it for a short range.
So if you don't care about that, what's going to happen is I actually have a coworker who, 30 years ago, was developing this transmitter at his house. He lived right across from the Ottawa airport, and he was transmitting signals. So one day, he got a nice visit from a bunch of people wearing suits, and they were from Industry Canada telling him to stop. And they actually fixed the radio for him, but other than that, they told him to stop. So what happens if you don't care is there's I think the Radio Act of Canada, and it's enforced by the RCMP, and you could get jail time. That's what happens if you don't care.
So you can't, like, there's no way to actually experiment with transmitting and receiving?
Get your ham radio license and then experiment on the specific bands. But if I was to, let's just say, have my little transmitter here and transmitting into Wi-Fi, and I would just kill everybody's Wi-Fi, everybody would be mad, right?
Is a license hard to get?
Yeah, you have to get a license to transmit in the Wi-Fi range. And basically all the chip manufacturers who make those little Wi-Fi chips on your laptop or PCs or whatever, they have a license to transmit in that band, right? So again, that would be something that's really bad to do because they can easily catch you. If they could catch you in the 1980s, they can catch you a lot easier now.
Is there any band that you can get just to experiment with? One that isn't in demand or in use by big companies? Or?
Yeah, it's the ham radio license band. So you have to get your license to know what you're doing, and then you can do that. And you can make your transmitters, you can make your receivers, you can make whatever you want.
All right, thanks.
Anyone else?
Hi. So you said you're not using matplotlib for plotting. You're actually using PyQt graph or something?
Yeah, PyQt graph. That's all the plotting I'm doing it on. It's really, the reason why I'm doing it, because it's really easy to integrate into Qt. And Qt is a very big GUI developing environment. And the other reason is that it's very fast. I mean, if you could sort of see, I'd say, according to their website, PyQt graph, they're much faster than matplotlib. So if you're talking about real-time signals where you want to just keep displaying as fast as possible, you don't want to miss anything, speed is the name of the game.
Any other questions?
So it's awesome that there's all this software available to do this kinds of experiments and work. On the hardware front, is there anything you would recommend or anything you'd suggest looking into other than the transmitter dongles, especially for biohacking? Is there anything that's worth checking
So
out?
again, the original intent was to actually do some biological signals. So I actually have an ENG amplifier, that's an electromyogram. You use it to amplify muscular. If you put two electrodes across your bicep and you flex, you'll get a voltage differential across the two with a reference to your elbow, and you can actually detect that signal. And you could do all kinds of things with it, like robotics or whatever. So if you go to sparkfun.com, they have a bioamplifier. They have a muscle. It's called a muscle sensor. They have a heart rate sensor, which is this thing. And I also bought this pulse sensor from there too. So that's one to start. Get an Arduino and start using that, because you do need a microcontroller to at least read the signals. You can't use your microphone. I tried that, but the thing is really bad at very low frequency signals, unless you have a really good sound card. So yeah, just look into the hobbyist websites.
Anyone else? No? Okay. Thanks a lot, Mohammed.